Dear students, today I am going to discuss Module 3, Induction Motor Drives, Analysis of Induction Motor Fed from Non-Sinusoidal Voltage Supply. So here in this topic, we are going to discuss about induction motor is fed from non-sinusoidal supply. Non-sinusoidal supply voltage is nothing but square waveforms. Okay, and here generally this kind of application we are using for the speed control of induction motor by using variable frequency drives, then inverter. It is given to the inverter, then you will get the non-sinusoidal supply. Okay, and how we are going to control the speed using drives means by using voltage to frequency method. Okay, so generally if you want to discuss a non-sinusoidal waveform, we are going to do the analysis using Fourier transform. Okay, using Fourier transform we are going to do the analysis, and here the Fourier transform can be used for both periodic as well as non-periodic signal. Okay, so it can be periodic signal or it can be non-periodic signal. And now here the fundamental, first we have to take the if you want to do the analysis, if you want to do the analysis of the harmonics, first I'm going to take the fundamental pace component. Okay, the fundamental pace component, these are the pace component with respect to neutral. Here A pace with respect to neutral, it is given by V1 sine omega t, and B pace with respect to neutral, V1 sine omega t minus 2 pi by 3, that is minus 120 degree, and your C pace with respect to neutral, V1 sine omega t minus 240 degree or plus 120 degree. Okay, so with all the pace sequence ABC. Okay, and now here generally we are all the even components, all the even order components. Okay, so here I'm taken only the odd order components, odd order harmonics, and the even order harmonics are automatically eliminated by using half symmetry property. Okay, because of half symmetry property, the even order harmonics are eliminated, and now here only I'm going to do the analysis on the odd order harmonics. Okay, so odd order harmonics, in that fifth harmonics and seventh harmonics I'm going to do analysis. Now with the phase voltages for the fifth order harmonics will be given by VAN equal to V5 sine omega t, VBN equal to V5 sine 5 omega t minus 2 pi by 3, or we can write it as here if you multiply this 5 equal to 5 if you take inside, and if you multiply 5 omega t minus 4 pi by 3, and here again this 5 for C pace with respect to neutral, again V5 sine pi omega t minus 2 pi by 3. Actually we know that here the concept, we know that the basic it should be equal to the basic fundamental. Okay, so see the V pace will be same. This is nothing but your fundamental component, the A phase with respect to neutral is a fundamental component, and the second one is minus 120 degree phase shift, the third one is minus 240 degree phase shift with respect to the previous one, or first one, not previous one, first one, or you can say minus 120 degree with respect to the previous one. Now here actually we have to, as per the fundamental equation, we have to bring this equation minus 240 or minus 120. How we can achieve these things means by multiplying minus 120 and then adding 360 degree, by multiplying minus 120 and keep on, you have to add 360 degree. Okay, keep on, you have to add so this fifth component, if you want to get minus 120 or minus 240, what you need to do to get this component, that is V5 sine 5 omega t minus 4 pi by 3, to get this one, because if you multiply 5 inside you will get a 10 by 3 you will get. In order to get minus 4 pi by 3, you need to do minus 120 into 5. Okay, minus 120 into 5, and then you have to add 360 degree to get this component minus 4 by 3. And same thing here also in seventh order harmonics also. Okay, so in seventh order harmonics, if you take with respect to the fundamental component, you are going to write this. This one will be same as that of your fundamental. VBN equal to V7 sine 7 omega t minus 2 pi by 3. V7 7 omega t. Actually 7 into 2 14 by 3. So what you need to do, minus 120 into 7 plus 360 degree in order to get to minus 2 pi by 3. So you have to do keep on, you have to multiply 7 into minus 120 and keep on, you have to add 360 degree in order to get this minus 2 pi by 3. Okay, that is you have to do, that is the trial and error method you have to do, and you are going to bring to these conditions like your fundamental phase voltage components. Okay, and now here we can say your fifth order harmonics are negative order harmonics with compared to fundamental component. If you compare the fifth order harmonics with the fundamental component, the fifth order harmonics are the negative component and your seventh order harmonics are the positive component, because the seventh order harmonics are in phase with your fundamental component, so that it is called a positive sequence component, and the fifth order harmonics are the negative sequence component. So this is out of phase with respect to your this one fundamental component. That's why fifth order will be called as a negative phase sequence, and the seventh order will be called as a positive sequence. Positive sequence. Okay, and actually how to find the harmonics, the fifth order harmonics and seventh order harmonics, which is positive or negative. And again this even order harmonics and odd order harmonics, again it is classified into positive sequence, negative sequence and zero sequence. The fifth order harmonics and seventh order harmonics, how it is positive, how it is negative, how it is zero, can be evaluated by using this m. Okay, m is equal to 6k plus 1 and m equal to 6k minus 1 and m is equal to 3k. By using these three components, we are going to find the negative sequence component or a positive sequence component. This mth order positive sequence will produce rotating field in direction of the fundamental okay, the fundamental component. Okay, the positive, the mth order, if the mth order positive sequence will produce the rotating field in direction of your fundamental at speed m times of your fundamental. Actually, generally, one more thing you want to know, if the harmonics are higher, okay, if the harmonics are higher means, you suppose for example, if you take fifth order harmonics, the frequency will be 5 times of your fundamental, but magnitude will be 1 by 5th time of your fundamental. Okay, if you take your fifth order harmonics, the frequency of the fifth order harmonics will be 5 times of your fundamental frequency, and your magnitude will be 1/5 of your fundamental magnitude. If you take seventh order harmonics, your frequency will be 7 times of your fundamental component, and your magnitude will be 1/7 of your fundamental component. Okay, so this is about your harmonics component, and here the harmonics voltages and currents will be taken by using this equation, m equal to 6k plus 1, m equal to 6k minus 1 and m equal to 3k. This represents the positive sequence, this represents negative sequence, and this represents the zero sequence. Okay, now here generally the seventh harmonics, okay, the seventh harmonics will be 7 times into 1500 rpm. So the fundamental harmonics will have the speed of 1500, okay, 1500 rpm, okay, 1500 rpm. So the seventh order harmonics will be having 7 into 1500 rpm. It will rotate in that speed. The mth order negative sequence will produce a rotating field in opposite to the direction of the fundamental speed. Okay, fundamental motion, fundamental component motion, and the zero sequence component which has no phase, so no rotating magnetic field. Okay, the zero sequence component has no phase, there is no rotating magnetic field. And the next class we will discuss the harmonic equivalent circuit of your non-sinusoidal waveforms. Okay, thank you students.